Welcome everyone to this RSS Sheffield Local Group seminar. We've got James Murphy with us today from the Hadley Centre at the Met Office. Similar to the Met Office's definition of a baseline, James, I believe, joined the Met Office in 1981.
I'm a walking baseline, yes.
And moved into the Hadley Centre and is now the scientific strategic head. He's led a number of teams to develop new initiatives for the projections of climate change, particularly in the area of uncertainty quantification, which I'm sure everyone at the RSS is obviously interested in. I'm going to hand straight over to you, James, and thank you very much for giving us your time.
That's a pleasure. Thank you very much, Alison. So what I'm going to talk about today is the UK climate projections. So these are the UK's national climate change scenarios currently produced by the Met Office. And my particular role at the moment actually is to be the sort of project manager of the land side of these climate projections. So that's going to be mainly what I talk about today, but we'll split the talk into really three different sections. So the first is a bit of an introduction where I'll talk a little bit about the scenarios we produce and what products go with those, and also a bit about just a little bit about the basic climate modelling setups that go into producing this data. And then in the middle section of the talk, I'll spend a fair proportion of it in illustrating some of the uses of the UK climate projections for assessing climate impacts, understanding future risks, and informing decisions about climate change adaptation and mitigation. And then in the last part of the talk, this is going to be my red meat to you statisticians, where we'll talk in a little bit more detail about one of our products in particular, which is a set of probabilistic projections that we produce, focusing in particular on how those play out for a selection of extreme events. And hopefully we can just illustrate there in a little bit more detail some of the statistical processing that we apply to derive some of these products. So to start off with, here's a sort of very kind of top level strap line of what the UK projections are all about. So we provide up-to-date assessments of how UK climate may change in the future. And the information in particular supports national risk assessments and adaptation plans. And these are produced by the government on a 5-yearly timescale following the auspices of the Climate Change Act passed in 2008. Now, the sort of very appetizing looking pie on the right shows the different types of information that go into the scenario. So firstly, and very importantly, there's a set of observations from the National Climate Information Centre, and that's very important for establishing the level of current climate variability and risk on which the climate change projections then build. Then another key component is a set of marine projections, which include things like sea level rise and future changes in storm surges and things like that. I'm not going to talk about those today, but they're a very important component. And then the other sections of the pie relate to various components of the land projections, which I will say something about. And I'm going to hopefully uncover, some of the kind of complex ranges of things that we can use the projections to get information about. But if we wanted to reduce the whole operation to a couple of strap lines, we might say that UK CP indicates a greater chance of warmer, wetter winters and hotter, drier summers over land. And while for the marine projections, we say that sea level rises have already been rising and will continue to rise in the future. However, today, as I've said, I will focus mainly on the land side of the projections. So moving into it then, this first slide is just a little bit of a cartoon about the climate modelling on which the scenarios are based. So we use a lot of global climate modelling to produce the scenarios, and they simulate both atmospheric and ocean circulations on 3-dimensional grids. And then in addition to that, we also use a couple of limited area setups of our model to derive more detailed information at finer spatial scales. So for the modelling that we produced at the Met Office that fed into the latest set of UK scenarios, which were published in 2018 and 2019, we used global climate models, which had a horizontal grid spacing of around 60 kilometres in the atmosphere with 85 vertical levels. And then that was coupled interactively to a dynamic ocean. And we use those to predict both the large-scale atmospheric circulation and patterns of global warming, and also patterns of change in ocean conditions, including sea surface temperatures. And then what we do is save the output for those and then use those subsequently to derive what we call nested simulations of regional atmospheric models. And in these, we actually prescribe changes in sea surface temperatures taken from global climate runs that we've already done. And we also prescribe time series of atmospheric circulation at the lateral boundaries of these models. And we do this for two domains. One is a European 12-kilometre domain, which can then be used to look at detailed impacts across the whole of Europe. And then we use results from that to drive a further nested simulation of a very high resolution 2.2 kilometre domain for just the UK. Now, one thing I want to make at this point is that even at that very fine 2.2 kilometre resolution, there are a lot of key Earth system processes that determine the climate which cannot be resolved at the grid scale. So a key component of all climate models is a set of what we call parameterizations, in which we use grid scale variables to infer various important sub-grid scale phenomena such as radiative transfer, cloud formation, and rainfall. And those equations inevitably involve various expert-specified parameters that control the outputs of these schemes but are uncertain. So I just want to get that out there early because I'm going to come back to these questions of parameter and structural uncertainties in climate models when we get into how we represent uncertainties later in the talk. So going now into the components of the land projections, just a few slides to illustrate what some of these look like. So one of the components is a set of probabilistic projections, and the primary purpose of these is to provide the main, not the only, but the main source of information on uncertainties in these UKCP scenarios. And because they are the main tool to represent uncertainties, we use a particularly large set of climate model simulations to derive these. So these PDFs are based on around 350 climate model simulations. And they're available for 5 different scenarios of future emissions of greenhouse gases. So one of the key sources of uncertainty in this whole process doesn't come from climate modelling at all. It comes from socio-economic modelling of different pathways for future greenhouse gas emissions. So what we actually do is provide our projections for a set of these. And a couple of these are illustrated in the plot on the left, where we're looking at time series of future rise in global average surface temperature, perhaps the most basic climate variable of all. And one is for an emission scenario called RCP 8.5, which imagines a fossil fuel intensive future world. And you see there, and what you're looking at here is a plume, which represents how the width of the PDFs evolve over time as uncertainties develop and global warming also develops. And the white line shows the median of these PDFs, and you can see that by 2100, under this intensive scenario, we're reaching levels of global warming approaching 5 degrees as a central estimate compared with the historical baseline period, which here is 1980 to 2000. But as I said, we also provide these scenarios for more moderate emission scenarios, and the lowest one that we currently include is called RCP 2.6, and that one includes strong mitigation measures. And for that, we also see a range of possible outcomes for global temperature, which derives from the modelling uncertainties that we put into these PDFs from these 350 simulations. But nevertheless, even these show significant rises in future global warming, and the median there amounts to something between 1.5 and 2 degrees by 2100. But as well as for global mean temperature, we provide these PDFs for a range of variables at the UK scale. So this is just one example showing changes in precipitation over Scotland for the 2070s, in this case under RCP 8.5, just to see what these PDFs look like at the UK scale. And here the blue curve shows you what a PDF of changes in 20-year average winter rainfall looks like. So this is expressing an uncertainty range for what future climatology of rainfall might look like over a 20-year period. But what we also produce the projections for are for individual years. And the advantage of doing that is that you can then factor in the additional effects of interannual natural climate variability from year to year. And when we do that, we can see an even broader PDF, which includes these interannual variations shown by the red curve here. And that's the sort of product that we would use to look at the risk, for example, of having extremely wet winters, which might lead to flooding conditions. So that's the probabilistic projections. Now, the nature of these is that although they're based on climate model output, they do involve, of course, a lot of statistical processing in order to convert those into summary quantitative estimates of future changes for a few selected key climate variables. Now, that is great for users who only need that kind of information to do their impact studies or to come to their decisions. But of course, for a lot of users need to have access as well as that to data which is more flexible, from which they can derive, for example, more complex indicators of climate change for use in more detailed types of impact study. And also there is a need for users to be able to kind of dig into the final quantitative results and to understand how those results came about. For example, to look at case studies or drivers of change that might occur via circulation changes in the atmosphere, say. So for users who need that kind of information, we also provide data sets which are based on raw climate model output without the processing that would convert them into things like PDFs. So one of these products is a set of global projections, and there are 28 of these, which consist of 15 different versions of the latest UK climate model. And we achieve those by perturbing some of these uncertain parameters in this model to get a range of outcomes that sample different representations of future climate change processes. And then we augment that by adding a further set of 13 international climate models, which contain different assumptions in how they are built to the Met Office model. And so we do that to increase the spread of plausible outcomes that users have available in this particular strand of information. And so, as I said, what this provides is a more flexible data set, which can be used, for example, to understand certain large-scale drivers of projected regional changes. And what we're looking at here is how the models show future instances of, for example, easterly circulation types of winter, which is the sort that typically leads to cold winters, versus westerly types of circulation in winter, which would lead to stormy conditions and moist conditions and perhaps an enhanced flood risk. And then we can see time series of how the loading on these two weather types plays out in the future. And the heavy red curve here shows the ensemble average of the ensemble of Met Office runs, which tends to show a slight reduction in the future in the easterly weather type and a slight increase in the average loading on the westerly weather type. So that might be good for assessing what might happen under stormy type of conditions, if you like, in the future. Whereas the international set of models don't show a strong signal of change in the balance between these two weather types. So they might be more suitable for looking at examples where the opposite occurs and we continue to see these easterly cold regimes in the future. So that's the global data set. As I said in the modeling cartoon I showed a couple of slides ago, we also have a set of regional projections which are run at 12 kilometers for Europe. And the new thing that we provided for the first time in the last set of projections was a set of very high resolution 2.2 kilometer simulations for Europe. So this is just a slide about that. Now, the key thing about this particular product is that at 2.2 kilometers for the first time, we can actually explicitly resolve the dynamics of large convective storms. And that's particularly important because once we can do that, we can start to generate plausible information on how rainfall might change, not just at the seasonal and daily timescale, but also at the sub-daily timescale. We can start to get down to hourly rainfall and also things like the severe wind gusts that go with extreme convective events. And what that means is that in turn we can start to say something, for example, about flash flooding and how that might affect urban areas. So this is quite an exciting development, we think, and a strand of new capability that we were able to add in the last set of projections. And for this, we have 12 simulations available, run for 3 different time slices in the future, just for one emission scenario. And I'll say something a bit about some of the applications of this data in a moment. But before I get to that, I wanted to kind of show this slide, which really is looking at how the different types of information compare with each other, and just say a little bit about how users might use them together. I hope I've communicated that there's a fairly rich range of data available in these UK climate projections, but they do have different strengths and limitations, and they are provided inevitably whenever we produce projections at a certain time at a different stages of development. So what we're looking at here is future changes for London in summer temperature and summer rainfall for the 2070s relative to the baseline under the high emission scenario. And we're looking at what all the different types of information is saying. So the boxes and whiskers are showing us the wide uncertainty ranges that the probabilistic projections produce. And then the orange and the blue dots are showing us what the global projections produce, where the orange dots show the Met Office model results, and the blue dots show the results from the international models. And what you see, both for temperature and rainfall, is that when you combine the Met Office results with the international results, you can again get a wide range of outcomes that are broadly consistent with the range given in the probabilistic results, but that you really need both of those ensembles together to achieve that. So on its own, the Met Office simulations tend to populate the high end of the temperature response because they have rather a high global climate sensitivity. Whereas when we look at rainfall, they tend to populate the dry end of the possible range of rainfall outcomes. And that's important because where we got to in the last set of projections was that we developed the ability to drive the more detailed regional information shown in the pink dots at 12 kilometers and the green dots at 2 kilometers from the Met Office models. But we still have yet to reach the point where we can add in simulations of these more detailed results driven by other international models. And I should say that in itself, the ability to have a range of these 2.2 kilometer results was a big step forward, because prior to this, the only information at that sort of scale that had been available had been from one-off simulations published in journals, but never really before served up to users in ensemble format. So that was a big step forward, but there's still some way to go into providing this sort of type of information in a way that covers a full range of outcomes. So what we hope that users will do is, when they're using this detailed information, which is great for looking at high temperature and dry rainfall outcomes, is to bear in mind the wider context that there are other possible outcomes that could also occur, as shown by the other products. So that's just an example of how we hope users will use all the products together to kind of gain some context for the impact studies that they're making. So, having made that point, I wanted to go into the next section of the talk, where we look in a bit more detail at some of the applications of the data to actually assess impacts. And here, my aim is just to give you a broad sense of what a broad range of studies are being done with the data. So the first thing is just a few statistics on usage. So we have 2 main data portals for the data. One is called the UKCP user interface, and this really provides a kind of summaries of the most frequently requested variables, and it is also the place where users can go to get rapid maps and plots showing some of the results. So users of the probabilistic data tend to take their results mainly from this user interface. So when you look at how the usage is broken down, the probabilistic data tends to dominate, although the other types of information are also downloaded from here. And then if you look at the range of sectors of users for the user interface data, they are really spread across quite a wide range of applications, from biodiversity to buildings to energy to water resources, etc. Now, the other source of information is called the CEDA archive, the Centre for Environmental Data Analysis. And this is really a data where a wider range of variables are made available. And this will be in particular where users who want to do more processed work, where they derive their own climate indicators and look at the effects of their changes perhaps in greater detail. That's where those sorts of users would go to get a lot of their data. So in this case, we see that the downloads tend to be dominated more by the global and local projections, for example. And you see that university users of the data who would want to be use it, for example, to do more detailed impact studies, perhaps, or studies where they look into understanding the changes that have occurred. That's where a lot of those users would go to get to the data, and also a lot of commercial users as well. But overall, when we add everything up, we can see about 10,000 users have access to data so far. So it's certainly the case, I think, that these data are being widely used across the two sources. So what I'm going to do now is go into some more specific examples of the usage. So I'm going to start off with an example where the high resolution 2.2 kilometre simulations are being used. And this is an application coming out of the UK Climate Resilience Programme, which is aimed at looking at providing guidance on how climate change will affect urban drainage designs and surface water flood modelling, surface water flooding in urban areas. And what tends to happen in this sector is that they tend to design a historical time series of rainfall events and then look to apply what they call uplifts, which are intended to add the impacts of climate change on what the extreme events in the future will look like. So what the map shows here is an estimate of a future return level for a 30-year daily rainfall event and how that might change across the UK. And you can see that on average, we're looking at an increase of 14.4%, but then there's a pattern to how that changes around the country. Now, this is based on results from around the whole year, but you tend to find that for daily rainfall events, the events which give rise to the most extreme events tend to come from moisture-bearing synoptic storms in winter. So you tend to see high values along the western coasts here, down the UK, for example, as well as across the south of the country as well. However, because we're now using these new 2.2 kilometre simulations, we can also start to look at corresponding results for uplifts in hourly rainfall extremes, which is something we've not been able to do before. And this now is a corresponding map showing the same 30-year return level uplift, but now for hourly rainfall. And we can see that now as a UK average, we're getting an uplift of 23.6%, so somewhat higher. And also, interestingly, from a physical perspective, we're actually seeing a different pattern, where actually the biggest increases in the future tend to occur in the north, over Scotland and northern England. And that, we think, is because the events in summer are dominated more by these summertime convective storms, from which we can now get this hourly information from the 2.2 kilometre modelling. And the biggest changes tend to occur in the future, where increases in temperature are accompanied by the highest increases in moisture availability. It tends to be in the north of the country where we get both those two things going together, and hence where we get the largest increases in the future. But as well as looking at high rainfall extremes, it's also important that we look at low events as well, so drought events. So here's another example from some work by Alice and Kay et al, looking at future river flows in various catchments around the UK. And in this case, they've used the probabilistic projections, because here the wide range that you get in those is very useful for being able to look at both high flow events, which is indicated by this Q5 metric here, and also low flow events, which is indicated by the Q95 metric. And what the whiskers are showing in red here are the range of outputs they get from the probability distributions in the latest set of results for various catchments. So, for example, for the Avon catchment, what we see is that for low flows, there's a broad uncertainty range, but the PDFs do suggest a reduction in low flows, suggesting an enhanced risk of drought conditions in the future. Whereas if we look at high flow events, there's actually a very broad range of outcomes which encompass both increases and reductions. But most of the PDF does suggest an increase, and at the top end, there's clearly a risk at the sort of 5 or 10% level of a quite substantial increase in high flow events and therefore flooding events as well. And just shown on the right there is another example for the Thames as well. So that's just another example of the kind of information that we can get out looking at both drought and flooding. And this one is another example, now looking at an agricultural type of impact. So this is from work by Freya Gary and colleagues at the Met Office. And what they've actually done is use the 12-kilometre regional simulations in this case. And they're looking at, in this case, at compound events. And so the driver of these particular types of risks are instances of high temperature associated with high humidity. And they looked at the impact that that has both on heat stress in cattle, which is the red information here, and also on potato blight, which is the brown information. And what they're doing here is highlighting areas of the UK where the biggest increase in heat stress days for cattle occur. So these tend to happen along the west of the country, largely because that's where we have the highest density of cattle, actually. And then also they're highlighting the 5 areas where the biggest increases in potato blight occurs. And of course, they tend to be where the most potatoes are grown. And then we impose the heat and humidity patterns of climate change on top of that to derive the impact. So another obvious example of climate change impacts is on heat waves. And of course, we've seen very good example in summer 2022 of why that's very important. So here I've chosen as an illustration some work by Nigel O'Neill and colleagues on future changes in the risk of having at least one heat wave annually in each country of the UK. And this was information that went into the latest climate change risk assessment in the chapter on health, communities and the built environment. And another useful thing about this slide is it also illustrates one of the ways in which the risk assessment is now looking at climate change. So as well as looking at scenarios of how warming progresses through the century under a particular emissions pathway, they're also becoming increasingly interested on understanding what levels of climate change we might see in the UK for certain specific global warming thresholds. So here, Nigel and colleagues have looked at a 4-degree warming threshold, which is what the pink results show, and also a 2-degree threshold, which is what the green results show. And what these results are showing are uncertainty ranges for the chances of having at least one heat wave and how they play out through time under scenarios which reach either 2 or 4 degrees by the end of the century. So you can see, for example, over England, that there's currently about a 40% chance of having an official heat wave by the Met Office definition in the current climate. But under the 4-degree scenario, by the time you get to the end of the century, it's almost certain that we get at least one event per year. Whereas under the 2-degree threshold, the risk also increases substantially. But the central estimate of the risk remains below 100% by 2090, but with a considerable uncertainty range. Then if you look for the other countries, under the 4-degree scenario, the risk evolves significantly for all countries of the UK, but the central estimate is slightly less than in England. And similarly, under the 2-degree scenario, we get lower increases, but still substantial increases with an uncertainty range there as well. So another interesting example, and this is now returning to the 2.2-kilometre simulations, is climate-related subsidence. Now, this is something that's a risk throughout the UK, but it's a particularly strong risk in London, and it arises from shrinking and swelling of clay. driven, and what this study is looking at is the effects of climate change and how that might evolve in the future. So in London, we already have a substantial risk. So about 20% of properties are already at risk from this climate-related subsidence. But the projections show that by the time we get to 27, that increases significantly to over half of all properties. And it's quite interesting because this is affected by two different aspects of the projections. So I've talked about how on average over the south of England, particularly in the summer, the projections are characterized by a large future warming, but also by drying in the level of average precipitation. So that, of course, tends to lead to enhanced drought conditions and shrinkage of the clay, which is one risk on subsidence. But what I also showed in the hourly results in particular, that at the same time, the variability of precipitation increases. And actually, alongside the average drying, we also get an enhanced risk of short period rainfall extremes as well. And that is the sort of thing that can lead to swelling of the clay by saturating the soil as well when the conditions are right, which also contributes to increased subsidence. So I think that's quite a nice example of how different aspects of the projected changes combine together to influence the impact of interest. So just a couple more in this section. As well as these more detailed studies of impacts, another role of the projections is to provide more sort of high-level information, which are used for sort of education and outreach purposes. And another one of the UK Climate Resilience Programme projects which does that is one called City Packs. And what this does is assemble some key top-level information about climate change for use by urban planners and for dissemination to the general public, to educate them about what climate change factors they will need to think about in the future. So it includes kind of qualitative discussions of how climate affects their particular city. It includes also information on observations of past climate change and how climate change has already affected the climate they live in. So this is an example where the famous climate warming stripes that have been developed by Ed Hawkins at University of Reading are used, and they provide a nice visual illustration of how climate change has developed already. Then there are discussions about potential climate impacts in the future and the effects of different emission scenarios. And there are also some key results provided from the probabilistic projections in this case, which illustrate some particular numbers for how rainfall and temperature might change in the future. So that's an example of a more sort of top-level outreach type of project. And here's another one, which looks at another aspect of communication, which arises from using examples of recent observed weather extremes when they occur to say something about how those types of events might play out in the climate of the future. So in this particular example, we're looking at a recent record UK winter temperature, which occurred in late February 2019 at Kew, where a temperature of 21.2 degrees was recorded. And that was particularly notable because not only was the previous record broken, but it was absolutely smashed. So it was about 1.5, this temperature was about 1.5 degrees, I think, warmer than the previous record. So that creates an interesting communication challenge where clearly climate change may have played some role in driving that event, but climate change on its own cannot have caused the event in its entirety. It must also have been down to a particularly unusual circulation that occurred on the day, and that was indeed the case for this observed temperature record, which involved a very strong southerly flow of air all the way up from the Canary Islands and Northern Africa. But what we can then do is to look into our climate model projections to identify historical records in those as well, and then look at how long it takes for those to become more commonplace events in the future as one way of communicating the effects of future climate change. So this was in a paper by Mike Kendon et al., published recently. And what each of these panels show is an example of time series of the hottest or warmest winter temperature in each year, all the way through from 1900 through to 2100. And this uses the global climate simulations. And in each case, the horizontal dotted line shows the record that was found from the historical record, from the historical part of the runs in each of these simulations. So in each case, you get a record, and in some cases, this record was established by an event which was only slightly higher than other extreme events in the record. Or in other cases, like this one here, you get an example where the historical record was way above any of the other previous events. So a bit more like the sort of event that we actually observed in Q in 2019. And then what you can do is look into the future component of the runs, where you can see clearly the effects of global warming on influencing the trend of future warm winter days. But in some cases, the historical record was so extreme that it takes until the late 21st century before we actually start to see new records being set. Whereas in other ensemble members from these simulations, where perhaps the observed historical event wasn't so extreme, we see this record being broken frequently and and quite soon in the future part of the projections. So what Mike and colleagues have done in this bottom plot is to synthesize all that information to give a more general picture, which actually shows that typically a historical record won't be exceeded regularly, even under climate change, until after 2050. But by the time we get to the late 21st century, they are becoming more commonplace events that we might expect to see more or less every year. So again, that's another nice way of communicating how some of these historical and notable weather records relate to future experience that we might expect to see. Okay, so in the final section of the talk, I'm going to kind of back up from that and go into a little bit more detail about some of the statistical methods that we use to derive some of our information. And for this, I'm going to use the probabilistic projections as an example, and in particular, an application of this that Simon Brown, myself and Glenn Harris developed about a year or so ago, to extend the probabilistic projections to look at certain examples of rare daily events. So, from a statistical point of view, this is hopefully quite interesting because we combine the Bayesian framework that we use for the probabilistic projections in general with some extreme value theory to derive the projections of the rare events. So, leaping straight into it, the first thing we need to do is just back up a bit and remind ourselves at a basic level about sources of uncertainty that we need to account for in these probabilistic results. So I've talked already about how emissions are one source of uncertainty that lie outside the climate modeling. So when we build PDFs of the response, what we're doing is building PDFs in response to a particular emission scenario. We're not attempting to make a grand probability distribution that folds in all the modeling uncertainty that we think about with the uncertainty in the socioeconomic assumptions. But as I said earlier, what we do is provide these results for a range of emission scenarios. So users who do want to compare emissions uncertainty to response uncertainty can do that themselves if they wish to. So when we make probability distributions for a particular emission scenario, we're thinking about factoring uncertainties that arise due to natural climate variability, which might occur from year to year or decade to decade, and also to modeling uncertainty, which represents our own knowledge uncertainty about how to build climate models and then get those to simulate the various processes that combine together to drive climate change at a certain level into the future. So as an example, I'm just showing here some time series of global mean temperature change as it plays out in a number of climate model ensembles. So the orange curves and the blue curves represent the global projections I've already talked about from UK CP18. So the orange ones are the Met Office results, which tend to show relatively high levels of global warming. And then the blue results are the other international models, which tend to show sort of lower levels of warming. Both sets are plausible, and it's nice to combine them to get a more broad overall view of what changes we might see. Then underneath that is another set of grey curves, which shows a more recent international ensemble called CMIP6 that was run more recently to inform the latest IPCC climate change assessment. And that itself gives a broad range of results, which is kind of comparable with the results from the UKCP ensemble. But what I want to point out is that there's a fanning out of these uncertainties into the future, and that is due mainly to the modelling uncertainty that derives from the different assumptions made in different climate models. But on top of that, if you look closely, you can see the wiggles in the individual lines, and that is the contribution of the natural climate variability. Now, in the case of global mean temperature, that natural variability, which might arise from phenomena such as the El Nino Southern Oscillation, for example, becomes relatively minor compared to the modelling uncertainty, especially by the time we get to the late 21st century. However, for other variables, we might find a different balance between the relative contributions of the two, but it's important in these Bayesian methods that we account for both. So this is just a slide on the origin of modelling uncertainties to underpin the discussion of the Bayesian results. So as I explained earlier, climate models use these parameterizations of the effects of unresolved processes like cloud formation, in which they express the results as a function of grid scale climate variables. And that process involves both structural uncertainty, which might reflect to how the experts choose the structural forms for their equations that they use to make these linkages between the large scale and the subgrid scale results. And they also contain parametric uncertainties, which arise from values for parameters that they choose to control the specifics of that linkage within their own set of structural assumptions. And both of these choices are informed by physical insight, but they're uncertain. Partly due to a lack of observations of the relevant process and also to incomplete theoretical understanding of how best to represent them in models. So we have these concepts of structural and parametric uncertainties, and we can add also on the structural side other choices that are also structurally uncertain, and that might include things like grid resolution, the choice of dynamical integration scheme, and which set of Earth system processes we might include in our model, for example. Some are slightly more sophisticated than others in that sense. So when we assemble results from international collections of models, we're sampling structural uncertainties because each centre builds their models a different way. But what we also do in UKCP is add to that by building what we call perturbed parameter ensembles, which is where we take one model structure, in our case the Met Office model, and then perturb some of these uncertain parameters from the parameterization schemes in a more controlled way to generate a range of outputs that way that we can add to the multi-model results. And so in our particular Bayesian method, this is just a pictorial kind of summary of how that works. So on the left, we're looking at one of the signature climate variables, which are called equilibrium climate sensitivity. Now, this is the level of change in globally average surface temperature that we expect in the long term as a response to doubled carbon dioxide. So it's an idealized metric of climate change, but it's a signature benchmark of the level of climate change that your model simulates. And what we're looking at here is a histogram of results in green that come from a perturbed parameter ensemble of the Met Office model. So in this case, we had about 280 runs, so quite a large ensemble to get this histogram. And that provides the basis for our Bayesian method. However, even 280 simulations is not enough to cover all possible combinations of parameters. I think we perturbed about 30 parameters in these runs. So we also need a statistical emulator, which is trained on the green histogram of runs to predict results for parameter combinations that we have no model simulation for. So we then apply the emulator to get a more complete prior distribution of possible outcomes, and that converts the green histogram into this smoother green curve here. But then another crucial component of the method is to add in an estimate of structural uncertainty. And we get that by using results from a set of international models. And in this case, we have 12 international models, and their results are shown by the heads of these arrows. And the way that we get an estimate of structural uncertainty is by searching the parameter space of our own model across a wide range of variables to get the best physical matches that we can find to the results of each international model. So what we do is make these searches using a kind of gradient descent method. And then for each of the international models, we come out with a few best analogues, as we call them, which are these asterisks. And then we use those to predict the results of the international model. But the prediction doesn't work perfectly because the international model has different structural assumptions for our model. So by doing that, once we get one estimate of structural uncertainty, and by repeating it 12 times, we get a distribution. And then we add that into our prior distribution to get a broader range, and that's shown by the red curve. So that gives us our full prior distribution for this particular variable. Then, of course, the final key step is to convert that into a posterior distribution by attaching a relative likelihood to results from each point in parameter space. And the way we do that is by using a set of observations of the climate system to do that. So one of the sets of information we use is estimates of the climatological performance of the model in simulating past climate. And we have that available for a range of climate variables. And when we add that constraint in on its own, on this example on the right, we're showing, which is now annual global mean temperature changes for the end of the coming century, we convert the prior distribution, which is shown in red, into the orange distribution, which is somewhat constrained, but still shows a very wide range. However, in the total constraint that we use, we also use some additional metrics which relate to historical climate change. So we have a few metrics of historical climate change that have been observed that we also add into our likelihood function. And then we add, when we add all of those in to make the final constraint, we end up with the dark blue curve. So you can see here that by creating this posterior distribution, we've ruled out some of the more extreme outcomes in the prior distribution, but we still end up with a pretty broad range of changes for this particular variable. So that's a kind of whistle stop.
Sorry to interrupt you, James.
Sure.
I realised that we started late, but you told me that you wanted a 45-minute warning. So just to let you know, it's 5:02.
Yeah, okay, thank you very much. Thanks. Yeah, so I've probably got about, when did we actually start, Alison?
We started at like 10 past.
Okay, right. Okay, so thank you very much. So that's that. This is just a slide on the mathematics of this method. So this method is based on Michael Goldstein and John T. Rougier's framework, which is a general Bayesian system applicable to complex systems. And we've applied it to climate in our case. I don't think I need to dwell on this in particular, to be honest, but this is really just a simple summary of what this looks like mathematically. So you have the true climate Y, and then the climate model that you use to generate the perturbed parameter ensemble is F. The parameters are X. And then the structural uncertainty term, which they call discrepancy, is this epsilon term. Then you have a set of observations which have errors associated with them. And then you have the climate model, which estimates the climate model results, also with an error. And then the Bayesian process is integrating over this space X to construct a joint PDF of all the objects in the problem. And a key point of this is that these are multivariate calculations. So they allow us to produce mathematically consistent projections for a whole range of variables together, which is a really key aspect of what we need them to do. I'm going to skip over this slide in the interest of time. It's basically just to make the point that because we have a problem of very high dimensionality, where we're trying to predict changes for a whole different set of time levels every year through to 2100, for a range of different variables, a range of different seasons of the year, months of the year, and regions, then it's computationally not feasible to apply the full Bayesian framework to every variable. So what we do essentially is to apply it to a characteristic regional change expressed per unit global warming, which takes the dimension aspect, the time dimension out of that, and then apply another set of statistical emulation procedures to convert that into time-dependent changes, which gets us to the final result of regional changes at local spatial scales. So in the interest of time, I'll skip over the details of that. This is just a little pictures showing how some of these products look. So I've shown you already single PDFs that we produce for particular variables. Another key output is joint distributions, particularly of temperature and rainfall, that this method can also sustain. And that's important, for example, for looking at things like impacts like crop growth or drought, which depend on both temperature and rainfall. And then we have these time-dependent uncertainty plumes as well that we get out. And here's an example looking at regional rainfall change for the Yorkshire and Humber region. And here you can see that, again, we get these wide plumes in the 21st century. But because natural climate variability in this case is very important, as well as modelling uncertainty, even in the historical period, we see quite wide uncertainties in this particular example. So just in the last few minutes, I wanted to go on and say a little bit about how we extend this to get projections of rare daily events. So we use, there are various types of extreme value distribution we can use for this. So in this case, we use a point process distribution, which is controlled by location, scale, and shape parameters. That's just a little cartoon showing how you what the effects are of varying those parameters on how return levels vary with different return periods. But in the interest of time, I'll skip over the details of that. But an important part of this method is that in order to account for climate change, we have to parameterize how these parameters change in response to climate change. And what we've done here is quite a simple approach where we express the location and scale parameters as baseline values, which are appropriate for historical climate, plus future changes that are represented as a simple regression on global mean temperature. Whereas for the scale parameter, we found that that was so noisy, it wasn't really possible to parameterize that, how that might change in the future. So we simply assume a baseline value for that, although we do sample uncertainties within it. And this plot here just shows you an example of how we derive these parameters from particular model simulations. So just looking at this example, this is summertime temperature extremes over southern England from one simulation of time-dependent climate change. And what we do is use a peaks over threshold measures to calibrate the extreme value parameters. So this black line shows a threshold that isolates 3% of extreme events over the whole time series of the simulations. And then we train these climate change dependent mu t and beta t parameters on those. And then we can use those in particular case to see what that means for how a 50-year return level of temperature might change in this particular model simulation. So we get these climate change dependencies out for these extreme value distributions. And then what we need is to go back to the Bayesian method and produce probability distributions for these parameters from the large set of model simulations that we have available. So we then do that as well. So these are similar kind of steps to the ones I've just described, which show how we go from model simulations to prior distributions and then posterior distributions. But now for these extreme value climate change dependencies in location and scale. And then that puts us in a position to make probabilistic projections of extreme events. So just in the last couple of minutes, I want to bring this back to an event from recent climate experience. You will always, all I'm sure, remember the record-breaking hot temperatures that we experienced on the 19th of July, 2022, in which we exceeded 40 degrees over the UK at a number of locations for the first time. And this was a particularly kind of amazing event, really, was because if you consider the previous record temperature, which was 38.7 degrees, which occurred in 2019, that is shown by this little brown dot on the map of temperature values that happened on that day. Whereas on the recent event in 2022, you can see that that level of temperature was exceeded at multiple locations across the south and east of the country, all the way up to sort of Humberside, I guess. And what was amazing about it was how many locations broke the previous record, and then the dark brown patches are where we saw temperatures of over 40 degrees. So this really was another of those events where the previous record was broken by a lot. So this represents a really stiff test for our probability distributions of rare events, because you can ask the question then, can we capture that event? So to answer that, here is a plot showing 3 cumulative distribution functions for the daily maximum temperature in summer for London, and we're looking here at the 100-year return level. So the actual observed event for 2022 is shown brown, and in blue here is the distribution of possible 100 return levels that we get out of our probabilistic projections. And what you see is that the observed event is just about covered by the top end of the distribution. It comes in at about the 93rd percentile. So one interesting question we can ask is how much has climate change that we've already observed influenced the chance of that event compared with what we might have seen a few decades ago. So the black curve here shows a corresponding result for 1990. Now, since 1990, global mean temperature has increased by about 0.6 degrees. But what you see is that that's had a big influence on the upper tail of this distribution, because in 1990, the upper tail stopped at about 38 degrees, and the observed event for 2022 would have lain way outside it. So that's a kind of quite nice illustration, I think, of how climate change has made events like this possible, even though the event on the day, of course, was also influenced by an extreme atmospheric circulation anomaly that we saw on the day. And then just finally, here's an example of how this distribution looks in 2090 under the RCP6 scenario. And what you can see here is a much flatter curve showing that the influence of future global warming has opened up the possibility of much higher temperature extremes if we see a similar event in the future. So if we were to see another 93rd percentile event, according to these projections in 2090, it could come in at temperatures of up to 45 degrees. However, there is a lot of uncertainty associated with these projections. So at the lower end of the PDF, if the real world comes out more like that, then you could see somewhat lower values, more consistent with the 2022 event that we observed. So just the final slide to wrap up. I hope I've demonstrated that the UK projections provide a rich selection of data sets for analysis of climate change impacts, and that they're being used to inform risks and decisions across multiple sectors of the UK economy. We've included new capability, including in particular new projections for sub-daily rainfall extremes. And also, hopefully, we've seen that statistical methods play a key role in translating climate model output into quantitative estimates of future changes and their uncertainties. And among many things, perhaps one of our future priorities in the next set of projections is to develop all the strands so that they show full consistency between the ranges of outcomes that we're looking at the different spatial scales that we cover. So with that, I'll say thank you very much for your attention. Thank you.